I completely love this unit. I'm such a fan of rates and ratios. Ratios are truly the backbone of all of the math that is applicable to our daily lives. You care about it very much with your grades, what you get on the quiz, what you get on the test, what you get. I need that A, I need that B. That's a ratio. How much did you get compared to how much was available? Forrest walks in today and he goes, do you only teach 4 classes? Yeah. Because most teachers teach 5. I teach 4 because I have the department chair job and then extra responsibilities. So I really only teach 4 out of the 5. So that 4/5. I have 4/5 of the students, 4/5 of the grading, 4/5 of the copying, as my colleagues do, because I only have to prepare materials for one less class than they do. So when it comes to that workload, I have 4/5, 4 out of 5. Every single thing that you think about in real life is a rate. How much time do you spend on your homework every night? 30 minutes per night, 45 minutes per night, an hour per night, 2 minutes per night. And you can kind of correlate that to, okay, well, what grade did you get on the quiz? Because if you got a 30 out of 40, maybe you need to spend more time on your homework. Because that ratio, that for every, that out of, communicates a relationship. If I told you, oh my gosh, I have 8. You're like, 8 what? 8 what? Out of what? So our units become a really important thing. If I told you I have $8, would you think that was a lot? Depends on how hungry you are and if it was enough to buy a burrito bowl of Chipotle's, right? If I told you I had 8 dogs, what would you think? That's a lot of dogs, right? So the units become really important. What if I told you I had 8 kids? Oh, what is the matter with you? Right? That's a lot of kids, right? What if I told you I was out for 8 days? What if you had 8 classes with a substitute? That's a long time, right? Especially if I see you 1 out of every 2 days, another rate or ratio. Every time you communicate a rate or ratio, you're talking about a relationship, and knowing what those units are, give it meaning for us. My favorite unit to teach by far. When we talk about a part-to-whole relationship, we're talking about how much out of the total possible. When we're talking about a part-to-part relationship, we're comparing 2 parts. And we're going to bounce back and forth, and it's important for you to know, wait, is that a part-to-whole story, or is that a part-to-part story? Traditionally, part-to-part ratios are written like this. Traditionally, part-to-whole relationships are written like this, although you could flip it if you were smart and went ahead and used your units. Every time we put things in terms of a fraction and we use 100, we are putting them into a percent, per cent. Think of centimeter, century, that's 100. So when we talk about percent, that is the world's common denominator. Your mom understands a 94% on a quiz or a test. She might not understand 14 out of 15, right? If you come home and your mom says, how'd you do on that quiz? You're like, I got 14. 14 what? 14 out of what? 14 for every what? 14 per, like 14 what? So until you give that denominator, the fraction doesn't make sense. Until you give those units, that fraction doesn't make sense. All right, so we talked about some part-to-part and part-to-whole relationships. In this Herndon soccer, when we talk about the girls' wins and the boys' wins, and the part-to-part and the part-to-whole. So you need to make sure you're talking about whether you're comparing a piece to the entire or the 2 pieces together. When you're simplifying ratios, we have this conversation about dividing out a common factor. So if you expand 14 ABC and 2B times B, you can see that 14 and 2 are friendly numbers. We'll talk about friendly numbers if they're the same factors. By definition, a factor is a part of a number through multiplication. And if there's one b here and two b's here, then I can cancel one of those b's out because it makes 1. Anything over itself is worth 1, and I can simplify that out. In algebra last year, you should have learned a factor, something like this. It's a quadratic trinomial, quadratic because it's to the second power, trinomial because it's 3 terms. And you can break that quadratic trinomial down into the 2 factors that are multiplied to make it. And then you can cancel out one of those factors. So we get into this conversation about units and unit analysis, and it's kind of cool because when you talk about unit analysis, the biggest mistake that you'll make on your next quiz is somebody will look at that and I'll say simplify the ratio and they'll say it's 1/2 and they'll move on. Are they right? No, they're not right because I'm comparing 5 days to 10 hours. So when we do a unit analysis, what we need to think about doing is using a conversion factor. Now, I know because of my multiplicative identity that anything times 1 is equal to itself. So if I multiply this fraction by 1, I'm not changing the value. That makes sense to you, right? All right, so I know that in every 1 day, there's 24 hours. So what this lets me do is I know that then these days and these days, these units will cancel out. These hours and those hours will cancel out. So I can use my conversion factor to put everything on the same playing field, to put everything on the same parts of conversations. So if I'm talking days and somebody else is talking hours, we're like, wait a minute, we need to get on the same level. So this conversion factor says, hey, wait a minute, there's 24 hours in every 1 day. This is worth 1. So that then I can simplify this. Notice there's no equal signs, just simplifying expressions. When I go to do that, I recognize when I'm multiplying fractions is no problem, top times top, bottom times bottom. If I have a number that is friendly, I can cancel out. But notice then I end up with 24 over 2. So this ratio is either 12 to 1 or just 12. It's a simplified ratio. Somebody's like, okay, well, what are the units? There are no units. I've canceled them out. So we're talking about this is simplified down to 12 because it's not dependent on hours or days anymore. Those units I eliminated by using my conversion factor. Questions on these 4? The five tomatoes helps you remember how many feet are in a mile. Have you ever heard that before? 5 5 tomatoes. If you want to remember how many feet are in a mile, and that comic cracks me up because she's obviously supposed to be like European or something because he's got his little American shirt on. When I was in 6th grade, there was this huge push nationwide that the kids were going to learn, and we were going to switch over to the metric system. So for a while, they were looking at replacing the street sign and the highway signs with how many miles until the next exit or the next town with kilometers. And when I was in 6th grade, we spent a really long time learning about meters and centimeters and grams and kilograms and liters and milliliters, and it fizzled out because Americans are just too stubborn. We're like a dog that doesn't want to learn how to come or sit, or they just wait you out. So 36 years later, here we are, and we're still using feet and miles. You know, feet is some arbitrary measure. That was how long the king's foot was. You know that, right? That's how we got the foot. Oh. That's how long his foot was. I don't even know if I have a. Yeah. That's what it was. He has big feet.
Jesus.
That's how we have feet, y'all. Right?
That is
I know,
not
right?
good.
Right? That's a big foot. So there's my foot,
Jeez.
right? But so so then everyone's like other feet now. Like, wait a minute, let me try. So it's just one of those arbitrary things. So we need to watch these units and get them all squared away. Questions on that first page of notes? Okay. I love these, and I'm telling you what, if you get good with your proportions and switching around your means and extremes, it becomes so quick and easy to solve the next couple of units of what it is we're solving, because getting your x into the position that you want, you can flip-flop things all around. All right, if I have a ratio set up where I have means and extremes, and I'm going to come up and I'm just going to use this 2/3, 4/6 relationship. It's so important that everybody understands. First of all, are you all with me that 2/3 is equal to 4/6? Are you all with me there?
Yeah.
Okay. And notice, because if you want to know why that's true, you had a conversion factor, 2/2. 2/2 is worth 1. 2 times 2 is 4, 3 times 2 is 6. So this form of 1 is what you do when you come up with equivalent fractions. Our properties of proportions say that we can do cross products. So if I'm multiplying 3 times 4, that's going to have the same value as 2 times 6. You can do cross products, and the elementary school kids learn all the cute little butterflies. Did anybody grow up with the butterflies?
Oh, yeah.
Where you make the little butterfly, right? The cross products in elementary school, right? So that means that they have the same cross products, but what's really cool is you can come up with a bunch of other ratios that have this same cross product. I can put 6 here. Not the same story. Having 2/3 is not the same as having 6/3, obviously. But notice I still am with the same cross products. I can talk about 2/4 is equal to 3/6. Not the same relationship, but in your head, do the cross products. Same, right?
What? Wait.
Yeah? Do you see it?
Oh.
I can do 6/4 is equal to, come on.
3/2, yeah. Oh my
So
God.
it's a true relationship, not the same. So when you get a proportion, there's lots of different ways you can flip it around. Okay, first of all, means and extremes. The means are the middle parts, the extremes are the end parts. Here's your means, here's your extremes. When you do your cross products, you're always multiplying your extremes times your means. And that's how that cross products works. The reciprocal property says that if the two fractions are flipped, then they have the same cross products, and their reciprocals are also equal. So if I flip 2/3, I get 3/2. If I flip 4/6, I get 6/4. Our means and extremes can be flip-flopped. So notice I can change around where B and C are. Notice I can change around where A and D are, because I'm always going to end up with that same cross products. This is the one that's pretty cool when it talks about adding 1, because what I want you to see that is when you're adding fractions, this is really A over B plus B over B, C over D plus D over D. If I have two fractions with the same denominator, I can add their numerators and keep the same denominator. Which means if I can combine these, I can also split these. Does that make sense to you?
No.
If somebody gave you these two fractions, A over B plus B over B, because they have the same denominators, you would add the
A
numerators.
plus B divided by B.
A plus B all over B, yeah.
Okay.
Because this is worth 1. right? This is worth 1. So the reason why, God bless you, this proportion works is because my addition property of equality, I'm adding 1 to each side.
Okay.
Got it? Love it. Okay, our geometric mean, we're going to be playing around a lot with this. And it's a value for x such that this x represents the same value. So a divided by x is equal to that same x divided by b. When I do cross products, I get x squared is equal to a times b. So the definition of the geometric mean is the square root of the product of 2 values. That's kind of cool. All right. Homework. 1 key per table group. Talk about your homework. Go ahead.
When you're simplifying, when you find the square root, you have to, can you simplify it to a decimal? Or?
We're going to stick with a simplified radical. Okay. All right. 1 key per table group. Talk about it as a crowd. Go ahead. So was that homework that you checked last class? That's fine. But you checked it. And you got it right.
I have a question about this question. Like,
Because
I keep getting the answer, but I just keep guessing the answer. I like move around until I get the right answer. Is there like a formula that you have to use?
Okay. So watch this. These are the points. So this side is twice as long and parallel with this side. So if I'm going to say 1, 2, 3, 4.
It's like a rule of slide, if you have the corner and the image is like a stretch.
Small one. So this distance is this distance. So by counting, you know, away from this point, it's I figure out this 2 other points. So do you guys need the homework? Do you have it? Should you have it? Yeah. Did you check your answers?
Yes.
Did you check your answers?
The toy dump,
Okay.
a
You
real
guys
dump
check your
truck in real life
answers?
was much bigger
Yeah?
than it.
Did you guys check your answers?
So
You got this
when
homework?
the
Let me get
play,
you
the
one.
pen was
Did you get the papers that
when
you
the little
needed?
miniature one, the force was the same size as the dump truck.
Okay.
The dump truck.
Alright, so here's the deal. When we come back from having a sub, I don't know who was here. Like, I'm sure she took attendance. She didn't let me know. So I don't know who got the paper. Who did that? But guess how I will know? Guess how I will know who did the homework?
Because they have it, they made the effort.
How will I know who's done the homework?
Because it's.
The what? The quiz.
Oh, wow.
Yeah. So, you know, like truly when it comes down to it, of course I care if you've done the homework, but I don't care. Do you know what I mean? Because the quiz is going to tell me whether or not you know it or not. And then suddenly you care a lot when you get a bad quiz score. So if you care a lot after the quiz, you might want to start caring for the quiz. Because where do you want to make your mistakes? Okay, this is what you need to know, everybody. Listen, is Kevin on his phone? He is. Text whoever's, like, tell them this. Math is hard at whatever level you're at. Math is hard. Like right now, you think second grade math is, but those second graders are like, this is hard. Right? Are you texting it? Tell them, math is hard. No matter what level you're at, math is hard. You understand what I'm saying? So here's also, where are you going to make your mistakes?
Homework.
Classwork? Because
Yes.
then you won't make those mistakes again. Because you're paying attention and not texting and making a joke out of school. So maybe you're doing your learning during classwork. How about during homework? You do the homework, you check your answers, maybe that's where you make the mistakes. And you learn from them. Ask questions. Can you go over it? I don't get this. I wasn't paying attention. I didn't get it the first time. I was absent. Can you please help me do this? Absolutely, absolutely, absolutely every time. If you skip out on this classwork and the homework learning opportunities, you're making your mistakes on what?
Test.
The quiz. So fine, you make your mistakes on the quiz. Come in, We'll go over it, I'll answer your questions. So hopefully then you don't make mistakes on that. Math is hard at whatever level you're at, and you're going to screw up. Where are you going to make your mistakes? Classwork, homework, quizzes, tests, midterms, finals. The mistakes are going to happen. So your job is make them early, learn from them, so you don't make them again. See how that system works? All right. So let's talk about this. Solve for x. Your cross products are always going to be what you end up using to solve for x. So 8 times x, and make sure that anytime you have an algebraic expression, you bubble wrap it so that you remember to use the distributive property. Questions on 1, 2, 3, or 4? Yeah.
So when you're simplifying, you don't have to like double the 4 that you like 4x, but you have to double the 4. Does that make sense? Because
Which number? 1, 2, 3.
oh wait, never mind.
All right. Awesome. All right. Circle which problem above represents a geometric mean. Here she is. Because of these x's here. And then you solve that by taking the square root. All right, a scale model of a car is 10 inches long, 5 inches tall. The actual car is 60 inches tall. What is the length of the actual car? So the length of the car compared to the length of the model, the height of the car compared to the height of the model. But notice all these other proportions could also be written if I wanted to compare length to height of the car or length to height of the model.
It doesn't matter which way you put it.
As long as you're consistent and as long as in this example, your cross products had you multiplying 5 times x and 60 times 10. All right, in the diagram, it tells you what story, and keep in mind, this is code for the length from H to J, the length from G to K, the length from J to L, the length from K to L. So those are asking you for those distances, which you can then put in. 2 buildings shown have the same width to length ratio. Here again is your geometric mean. And then when Mr. Logan simplified this, 25 is a perfect square, 9 is a perfect square, 49 is a perfect square, and each of those can come out by taking the square root of them. When you're taking the square root of a value, your job is to break down the factors, looking for perfect squares, looking for double factors, things that can come out of the radical sign. Anybody need help with that?
Yes.
Okay. So Olivia says yes. Help simplifying. All right. So here's how I do it. Are you ready? If I'm solving this proportion and I have 105 over x is equal to x over 210, I cheat. Because I know that I'm going to be taking the square root of both sides. I'm not going to bother doing this multiplication because why put it together when you're just going to need to be breaking it down? So if I go to multiply 105 times 210, I'm grabbing my calculator and I'm going to get a number that's way outside my friendly numbers. I got nothing with that. That's outside my friendly numbers. My brain can't help me there. But here's where my brain can help me. I know that 21 is 7 times 3. So if I make this 7 times 30, are you okay with that math? Yeah. If I know that 30 is going to be, I can use 10 and 3, and then for here I can use 2 times 5. I've taken 210, and within my friendly numbers, I'm halfway through breaking down that number. Okay, this one here, 21 times 5, right? So I've got a choice here. I can keep going, 7 times 3, right? So now anything that's a double factor can come out of the radical sign. 7 times 7, when I take the square root of 49, I get 7. So my 7's come out. 5 times 5 is 25. The square root of 25 is 5. So they come out of the radical sign. What else do you see? 3 times 3 is 9. Square root of 9 is 3. So any double factor comes out as itself. Does that make sense? So if you look at what he ended up with, 105 times square root of 2. 7 times 5 is 35. 35 times 3, oh, there's my 105. So that's 105, and this is the only guy that's left. So I'm not going to worry about 10 or 30 or 21 because I broke them down and I'm using their end factors. So this is the only guy that I have left. Yes. Okay. All right. So this happens to me as a mother. The most frustrating thing on the planet is school pictures. I hate school pictures. Do you want to know why? This story. No, they don't. If you look at an 8x10 and a 4x6 and a wallet, none of those proportions are consistent. So if you order, if they show you the picture as a 4x6, when you go to translate that 4x6, it doesn't go into an 8x10. If you have a 4x6 portrait and you want to put that in an 8x what? It should be 12. Not 10. That's why your head gets cut off. There should be 2 more inches if it was in proportion. That's why if you look at this picture, look, she's so centered and so cute, so pretty. Doesn't she look nice now? Guess what? It's 2 inches shorter. We lose half her hair. Gone. So this one, if you order the wallet size, this 4x6, it should be 2x3. Well, 2x3 is not the same as 2.5 by 3.5. The whole thing is off. So because of those ratios, they're not consistent and your school pictures are a mess. All right, on the back. When making popcorn in a concession stand, oil to kernels is 2 to 3. And I want you to get used to having X be whatever factor represents how it's simplified. So I'm not going to do I'm not going to do 2 cups of oil to 3 cups of kernels. That's not going to get me. But what I can do is say, oh, whatever this factor is, like think about, you know how you double a recipe or you triple a recipe, right? So what ends up happening, if I want 25 cups, what should I do? I'm going to put 10 cups of oil and 15 cups of kernels in.
So when you don't have the numbers for the ratio, I guess, you would always use like what you have, like a 2 to 3.
Because that's the proportion that's right. Mm-hmm. So if you get a 93 out of 100 on a test, like you didn't answer 93 questions, right? So we ended up scaling it up by some values. So this X is going to be whatever factor is multiplied or divided to simplify the ratio. Mm-hmm. And that's what's great about this example with the lengths of the sides of a triangle. These are all part to parts, 1 to 3 to 5. These are all the parts. But my triangle isn't 9 because my perimeter is 18. So I know that X has a factor of 2. I simplified everything by 2, and that's how I got that. And down here we have some ratios to simplify. Go ahead, Maggie.
Triangle, isn't it not a triangle?
Oh, is it?
Or the first triangle.
The first triangle?
The 1 through 5 triangle. Okay, you just look over.
So if I had two, oh, it's not a triangle.
Oh.
Because the sum of my two smaller sides has to be bigger than my third.
Oh.
Go for Maria. Look at her being a thinker. I love it. I love it. There's a big brain on Maggie. She's feeling it today. I love it. That happens in geometry. Did you know that Matchbox cars are true scale models?
No.
Each car has a scale factor on the underside. The Porsche is 1 to 66. And the dump truck is 1 to 140. We don't use Hot Wheels because Hot Wheels are made up cars.
Hot Wheels are good.
Hot Wheels are made up cars. Every single one of these cars
Our real size.
has a ratio on the bottom.
This is not a real size.
Go ahead, reach out, play with them, touch them, look at them.
Ooh, made in Thailand. This is a 1 to 90. It has a 1 to 59 ratio.
Every single one of these cars has, pass them around, share them, around. Because I think James has the one that's the biggest. Okay. So, okay. So underneath on the bottom of the car,
It's on the top.
what? Well, mine here says 1 to.
Mine is 1 to 59.
This one is 1 to 59 also.
So I'll take
James, what's yours? James, I think, has the biggest one, the Airport Command Center. What's that one?
Cool.
One.
Those smaller than mine.
His is 1 to 114. Now here's what I want you to see. Here are these two cars. And I'll go ahead and I'll write down those ratios again for you.
What, yours is 159.
This car was, what was ours, Olivia? 1 to
159.
1
1
to
to 59, sorry.
to 59. And this one is 1 to 114.
Wow.
But do you see something unique?
They're about the same size.
What do you see from your overhead view? Is there any chance that these cars are actually in real life the same length?
No.
Because for every one unit here, how long is this car actually?
59 times
59. So if this car, if I get a centimeter ruler,
Are units always centimeters? Or?
and I see these ones are centimeters. And would you agree that 8 is an okay estimate?
Yes.
How long is this car in real life?
What's 59 times 8 even?
Who's got a calculator?
Calculate 5.
8 times what?
3.
Come on.
2.5.
8 times 59. So this car is actually 472 centimeters long,
What?
right? Yeah,
Oh.
right? Okay. So now when we talk about my command center, let's talk about my command center. We're also going to stick with 8 centimeters here, right?
Yes.
How long is my command center in real life?
I don't know. I'm guessing.
Ready?
5.
That's a big difference. right? So but why do they look like they're the same size now?
Because those would be small for children.
Yeah, because of all the little tracks that kids play with cars, and all the little carriers, all the little baskets you put them in. Put the car in your hand. It has to fit in your hand. So each of these models is a scale factor of a real vehicle, but having the different sizes changes the actual size because it's a different ratio. Does that make sense? Zanny, would you mind collecting my cars? No big surprise. Today's lesson is continuing along the idea of having similar shapes, shapes that have a constant ratio between them. So similar polygons are going to be polygons that are the same shape, but not necessarily the same size. So what I want to make sure you understand is that difference of congruence versus we're just going to have a symbol for similarity. Because when we have that equal sign underneath, this congruence is the same size and shape, and similarity is just the same shape. That same shape means that there's a constant ratio between all of the sides. Those side lengths are always going to be proportional, and that proportion is our constant ratio between all of the sides. We express that ratio as a scale factor, and a factor, remember, is something that's multiplied. So every time we talk about the idea of a factor, that's going to be something that's multiplied. That scale factor is the ratio of one shape to another. We can express the scale factor in one of two ways, and it can get confusing. So I want you to just listen carefully. If we write the scale factor as a ratio, I'm talking about the size of this compared to this. So my big car was, or James's command center, was 114 to 1. My big to my little. My scale factor can be written as a ratio telling me the story of their sizes compared one to another. If I write it as a scalar, and a scalar is a word when we talk about a value that's multiplied, if I write the scale factor as a scalar, what I'm doing is saying, what do I have to multiply this side length to equal this one? That scale factor as a scalar is going to be 2/3 because the smaller shape is 2/3 of the bigger one. The bigger one times 2/3. So we'll talk about this as we keep going. Our scale drawing or our scale model is that proportional representation. I saw it in the back. Is it you? Abdullah, hold up your calculator. Is it you, Owen? I thought I saw it in the back. Kevin, do you have a calculator? Kyle, do you have a calculator on you? I thought I saw it. Somebody here has a gray calculator. I thought I saw it. Would you take your cover off?
Wow, nice calculator.
Would you go stand by the door?
Get it, Krista.
Would you hold your calculator up, please? Other hand. Put it in the other hand. Do you see what I'm going for? Does he see it?
Probably
You're
not.
so observant.
Should we let him know?
Oh,
Christian, look at the door.
It's
What?
your calculator. Oh my god.
Right? Similar figures,
Different shapes.
same shape. Different what?
Ratios.
Same ratio,
Wait a second. Different size.
different size. Thank you, Christian. So we have the same shape, but definitely not the same size. That is an example of a scale drawing, or a scale model. Each of you held a scale model when you were looking at your cards today. Just like we were able to write a congruence statement, we're going to write similarity statements. This symbol here means similar. If I have all of my angles of a shape matching up and congruent to its corresponding one, if I have all my side lengths of a shape representing the same ratio, when I match up corresponding sides, I get this same ratio every time, then I know that my figures are similar. All right, so when we look here at number 1, let's talk about this. I have to decide whether the figures are similar. If something is similar, it's going to be the same shape. That means all my angles are congruent and all my sides are proportional. So when I talk about my angles, angle F is congruent to angle K because they each have these 3 bands. Angle G is congruent to angle L because they each have these 2 bands. Angle H is congruent to angle M because they each have these bands. Angle J is congruent to angle N. Keep in mind, angles are congruent, never similar. So your angles are not going to be similar. They're going to have the same measure. All right. When we talk about corresponding sides, I'm going to match up the side.
Thank you, Jesus.
Off to lunch. We'll talk when you get back. All right, so once we prove that the angles are all the same, we know that it's the same shape, but we need to know whether or not all the sides are in the same proportions. And we'll talk about how sometimes just the angles are not enough of a story for polygons. I'll wait till everyone's done texting and takes their earbuds out, puts their phones away. It's time to get smart, do some learning, put all those distractions somewhere else. So our next step is that we need to set up proportions to see whether or not these shapes are similar because their side lengths are in proportion to each other. So what we need to do is look for corresponding sides. If I look at this shape, this side length FG is joined by these angles that are marked by the 3 bands and the 2 bands. So I know that KL. So if I want to talk about the relationship of the distance from F to G and the relationship from K to L, I can say that that has an 8:6 relationship, and I can simplify that to 4/3 by dividing by a factor of 2.
So that's how you find out the ratio.
That's the ratio of the sizes of the shapes. Now I have to be consistent in how I write the relationships. So 2 things have to be true. I have to be comparing corresponding sides. And as I do my next 4 sides, I need to make sure that I go big to small. So the distance from F to J, I'm going to compare to the distance from K to N, 12 to 9. And that also simplifies to a factor of 4/3. With your group mates, match up the next 2 pairs of sides and see if they have a 4/3 relationship. Go.
Yeah.
So if you're doing it, you're talking out loud, you're matching up sides, and you and your group members are making sure you know what you're doing.
I got one. You ready for me? GH over L equals 16 over 12. Translate that to
Be the same, except for all, if you do small to big, you have to do small to big on all of them. And you're starting with the 3 to 4. I already got it.
No.
JH equals
The one I got.
JH over,
So,
and over here,
let's see mine.
quotient over 15, what does that equal?
Wow.
Oh, no, not one of two.
What's the kid?
All right, let's come back. So hopefully with each set of sides, you ended up with a fraction that you could simplify to 4/3. Because those proportions are all the same, you can write a similarity statement. So that you can say that quadrilateral FGHJ is similar, that's what the similar sign looks like. Notice it's without the congruence, no equal sign. It's going to be similar to quadrilateral. And you have to list them in corresponding order. If I start with F here, I have to start with K. And you name your shapes and ring around the rosy order. So if I go from F to G, I have to go from K to, and then to, and then to, yeah. There's your similarity statement. All right, so we've got, go ahead.
So if I, for the first one that you did for the set of proportions, is it okay if I did 6 to 8? But I have to do it for the rest.
So if you did 6 to 8, then you need to do 12 to 16 and 15 to 20 and 9 to 12.
Okay.
And your story here will be 3/4 instead of 4/3.
But they're both right.
But you have to do it consistently in the same order. If you go big to small, you have to do it for all of them. If you do small to big, you have to do it that way for all of them.
Okay, so if I got 3/4, it would still be correct.
Yeah.
Okay.
Okay, go ahead.
Does the square, like indicating the quadrilateral, does it have to be there?
Yeah, because you have to be talking about the shape. So if you wanted to write the word polygon, if you wanted to write the word quadrilateral, if you wanted to write the word shape, you would have to say what it is. This is just our little shortcut. Just like we draw the triangles before our triangle, we need to let everybody know that this is what it is.
It's not at the top.
It's not up here? Let's go ahead and add it. And you could go put Smarty up.
Good job, Steve. I have a question. So if you were to do like octagon, I guess, would you draw the octagon?
If you wanted to, by that point, I would just be writing shape or octagon.
Okay.
All right. So with these triangles, with your group mates, we need to recognize our 3 congruent corresponding angles. Let's go ahead and name this triangle ABC. And let's name this one DEF. And I know that angle A is congruent to what?
Angle D.
And I know that angle B is congruent to,
E.
and I know that angle C is congruent to, and that's all from these markings that I get from the diagram. In your minds, you should be thinking, if somebody's like, how did you know? Says who? It's from the diagram. All right, my 3 sets of angle or of side proportions, you want to list your sides that correspond. So once I say the relationship from the distance from A to C, what corresponds to that over here? D to F, and that's going to be a 4 to, uh-oh.
Oh no.
Let's talk about A to B, and what does that correspond to? D to E, and that would be, so 5 to 15, which simplifies to 1/3. And we'll talk about B to C to E to F. And that gives us, which simplifies to, so we can say, therefore, if X is equal to, what would X need to be?
Oh, 12.
How'd you get that, James?
Because if you multiply it by 4, it's 12.
Okay.
Wow.
So, notice he wants a 1/3 here. Look at the cross products. 4 times 3 is 12, X times 1, right? So now we can stick an X in there and use our proportion skills to solve for that. So if X has a value of 12, then triangle ABC is going to be similar to triangle DFE. If you want to get fancy, you could say by a 1 to 3 scale factor.
Yeah, it's
Look, ABC, what?
Oh my god.
Put another Smartie up. Yeah, we like that better, huh?
Yes, ma'am.
All right, next up. Here's our shortcuts. So, 4 triangles. And these only work for triangles. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the 2 triangles are similar. That's going to be our angle similarity postulate. All I need is the angles. I don't need to know the ratios of the sides. Next one. If I have all of the sides, then I have similarity. If the lengths of the corresponding sides of 2 triangles are proportional, then the triangles are similar. And notice I can set them up in this extended ratio with the stories of all 3 sides. Side angle side. If an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides including these angles, and this becomes so super important, it has to be that included sides. If the angle of one triangle is congruent to the angle of a second triangle, and the lengths of the sides including the angles are proportional, then the triangles are similar. So we're not going to put congruence markings here, because it's not about congruence. It has to do with the fact that each of these are proportional. So that conversation happens here if I end up with those sides being proportional. All right, so of course we're back to the idea of proving. So with your group mates, talk about 1 and 2. You mark a set, go. All right, so we'll go ahead and say, are these triangles similar?
Yes.
How come?
I know.
By angle similarity, I have these 2 right angles. I have these 2 vertical angles.
Yeah.
By the third angle theorem, I'm going to have those 2 angles also. So those 2 triangles, because every single side or every single angle matches up, they're guaranteed to be congruent. Now be careful, there is no angle similarity for quadrilaterals.
That's where.
And I'll show you why. If I have a square where all the sides are congruent and all the sides are right angles, nobody's going to think that that's going to be similar to a rectangle where I have all right angles and two sets of opposite congruent sides. So this similarity idea that we're talking about now, we're just focusing in on triangles, and you can prove two triangles are similar by either having at least two, by default then three angles similar, or by having similarity between all of the sides. So when I start talking about this, for each of these triangles, for the first time in our life, we can go ahead and go back to, we can judge by small, medium, large. I'm going to go ahead and identify the smallest sides of each triangle. And I'm going to see if they're in the same proportion. So when I look at corresponding sides, I can look at my small and my medium and my large sides of my triangle. So if I look at the sides of my triangle, are these two sides, 4 and 6, in the same proportion to their other sides of the triangle? So is the distance from here to here and there to there in proportion? So if I compare 4 to 8, I can look at 6 to 12.
Both 1/2.
So is there a story? Now, if you want to compare from triangle to triangle, go ahead and switch your means. If you want to say 4 to 6 and 8 to 12, that's fine. Let's go ahead and compare here. If I compare 4 to 6, can I also put this 6? If I'm comparing 4 to 6, and I'm comparing this 6, does that fit the 8 to whatever this medium size is?
No, it doesn't.
So which triangles do you think have a ratio between them that makes them similar? Constant ratios between the three sides. Which one, James? Triangle. Here, we'll go ahead and number them. 1, 2, and 3. You tell me which ones you think are similar.
1 and 2, because 4 and 6, that would be
So
2/3.
James says 4 to 6 is the same as, keep going.
2/3,
Okay.
and 10 and 15, also 2/3,
Mm-hmm.
and 8 and 12.
And 8 and 12 is also 2/3. So James says that triangles 1 and triangle 2 are similar. How about triangle 3? Why doesn't he work out?
It doesn't look like it.
Because why? Okay, so it doesn't have that same
It doesn't have a ratio.
2/3 ratio. And it's interesting because 6 to 6 is a 1-to-1, 12 to 12 is a 1-to-1, but this one's not. So it's going to have to be triangles 1 and triangle 2 that are similar. All right.